Welcome to Emergent Behavior, the AI podcast where we attempt to capture a snapshot in time as AGI clears the horizon. I'm your host, Prakash, also known as Adapi. You can find me on Twitter at numeric8, TEAPI. We are in a peculiar period of time in tech, Manhattan Project levels of investment in data centers, cries of bubble in the financial markets, cultish AI safety figures warning of the apocalypse. I hope to share with you the excitement, hopes, and fears of those on the frontier of artificial intelligence today. Join me as we try to figure out the truth of what the future will look like. My guest today is Professor Jason T. Wright. Professor Wright is a professor of astronomy and astrophysics at Penn State University and director of the Penn State Extraterrestrial Intelligence Center. His research focuses on the search for alien technosignatures, especially the telltale waste heat from hypothetical Dyson spheres, megastructures built around the stars to capture their energy. Professor Wright led pioneering surveys using NASA's WISE Space Telescope to hunt for mid-infrared excess emission from Dyson sphere-like structures. He is also known for his work on peculiar astronomical objects, such as Tabby's star, helping show its strange dimming was due to dust rather than an alien megastructure. In addition to SETI, Professor Wright studies exoplanets and stellar astrophysics, and he has been a vocal advocate for integrating technosignature searches into mainstream astronomy. My interest in Dyson spheres started off with a Dwarkesh Patel podcast with RLHF inventor Paul Cristiano. I will play a clip of the podcast just to set the stage for my discussion with Professor Wright.
Let's get more specific on what the timelines look for these kinds of changes. So the time by which we'll have an AI that is capable of building a Dyson sphere. Feel free to give confidence intervals, and we understand these numbers are tentative and so on.
I mean, I think AI capable of building Dyson sphere is like a slightly odd way to put it. And I think it's a sort of a property of a civilization, like that depends on a lot of physical infrastructure. And by Dyson sphere, I just can understand this to mean like, I don't know, like 1 billion times more energy than like all of the sunlight incident on Earth or something like that. I think like I most often think about what's the chance in like 5 years, 10 years, whatever. So maybe I'd say like 15% chance by 2030 and like 40% chance by 2040. Those are kind of like cash numbers from 6 months ago or 9 months ago that I haven't revisited in a while.
All right, Professor Wright, good morning, and glad to have you with us.
Good morning. It's good to be here.
So I'm going to just jump into definitions very quickly. The Dyson sphere was first kind of proposed by Freeman Dyson, and the idea is a group of energy collecting structures around a star. Would you say that is an accurate description?
Yeah, it is. In his original paper, he was hypothesizing a habitat. He was hypothesizing, just trying to think about what is the most extreme habitat an alien species might inhabit. And he imagined it would be a habitat that surrounds a star and uses all of the star's energy to maintain the habitat. That he refined that idea and kind of generalized it later. I think he kind of let go of the habitat part and just went to energy collection in general. And at first there was misunderstanding that he was imagining like a solid shell around a star or something like that. But he clarified what he meant was just lots and lots of structures in space that collect energy and do whatever the technology does with that energy.
Indeed. So because of the difficulties in engineering a solid structure around a star, I guess over time, Dyson sphere and Dyson swarm and Dyson shell have all become kind of interlinked as kind of like the same concept, basically.
Yeah, some people make those distinctions and they can be useful when doing things. But in general, it hasn't really been really formal. I refer to any large collection of technology around a star capturing a significant amount of its energy as a Dyson sphere, because that's the most common term for it.
And so the first thing is obviously, have there ever been Dyson spheres built, and can we detect them, which is your area of expertise?
Yeah. And we would love to know. One of the brilliant things about Freeman Dyson's idea is that such a thing would be extremely detectable. It wouldn't have to capture all of a star's light. Even if it only captured 1 or 2% of a star's light altogether, that would still be quite obvious. It would look quite anomalous, and we would, as astronomers, flag it as some sort of an unusual star. Now, many stars have material around them that has nothing to do with technology. Young stars in particular, the disk they formed from and that will eventually form planets serves much the same function as a Dyson sphere. The starlight hits that dust, and that dust gets warm, and then the dust radiates the heat away. And so we understand that young stars very commonly will have stuff around them, but older stars like the sun should not have very much stuff around them, just asteroids and some dust and stuff like that. And so any such star that showed evidence of warm stuff around it, we can flag as being interesting.
So I guess the WISE survey has done some work on this. There's been about 100,000 identified stars, and there's been a search in those stars for those technosignatures, emissions of infrared energy.
Yeah.
Yeah.
So the search for these things has been stymied by the fact that the way that you find them is that the stuff around the star gets warm because the starlight's hitting it and it collects the energy and that warms it up. And so you can look at wavelengths of around 10 microns or 20 microns for warm stuff around a star. And those wavelengths don't penetrate Earth's atmosphere very well. Earth's atmosphere is both opaque at those wavelengths and it also, shines at those wavelengths. So you really have to go to space if you want to make those measurements. And it wasn't until NASA's WISE satellite that we had a map of the sky at those wavelengths of sufficient sensitivity and sufficient quality that we could actually measure that for all the stars out there that we can see. So there are a lot of things out there. There are distant galaxies, there are nearby galaxies, and then there's all the stars in the Milky Way. And we can look at all of those places to try and see if there's too much infrared emission to be explained through natural processes. And so that was my work to use that satellite to try and do that search. So we started with the nearby galaxies because there's an idea that once a species is building Dyson spheres, it's probably interstellar at that point and can spread to other stars. And then why wouldn't it build Dyson spheres around all the stars in a galaxy? And that would be pretty obvious. A galaxy would really, really stand out if that had ever happened. This is called a type 3 Kardashev civilization or a type 3 species that is collecting most of the energy in the galaxy for its own purposes, for its technology. And we were able to show that out of the 100,000 closest galaxies to the Milky Way, there aren't any of those. We found some candidates, but they're almost certainly a well-known class of galaxy called a star-forming galaxy that just has a lot of stars forming, which kind of does the same thing. At Penn State, we are working on refining that search to put better limits on things so that if a galaxy had, let's say, only 1% of its stars covered in Dyson spheres, would we be able to tell that? And that's a much more subtle problem. It's tractable, but no one's worked on it before. And so that's something that our group is working on right now. Now, in parallel, we can look for single stars that might have a Dyson sphere around them. And that, in some ways, is a little more challenging. In some ways, it's easier. And there was a graduate student at Uppsala University named Matthias Suazo who did this for his PhD thesis. And he looked at millions of stars in the Milky Way and asked which of these have too much infrared emission and are not where we find young stars, not in nurseries. And he was able to show that if such things are around, they're extremely rare. There are very few of them in the Milky Way. He also came up with a list of 6 candidates, stars that, as far as we can tell, have no right to have any material around them, and yet still seem like they do. And actually, just the other day, I was looking at our brand new James Webb Space Telescope data from 2 of these candidates, where we've been using the telescope to try and see if that's really what's going on, or if there's some false positive that we can weed out.
So the WISE telescope goes up in 2009, correct? So before that, we had kind of a prediction of infrared emissions, but not really enough data to actually know for sure. Would that be a correct?
I would say, yeah, we didn't I mean, there had been infrared telescopes before, like
Yeah.
Spitzer and ISO and IRAS, that had looked at a lot of things, made some maps. What WISE gave us was an all-sky map of the whole sky at sufficient sensitivity, but also with a good enough image quality that we could pick out an individual star and say, yes, we know that that has infrared emission around it or not. The other big advance that let Matthias do his work and show that they're rare in the galaxy is, if you see a dot of light in the sky, it could be a distant quasar or it could be a nearby star in the galaxy. And if you don't know the difference, it's very hard to interpret what you're seeing.
Mhm.
And so that was the challenge I faced when I did this work. But the European Space Agency launched a satellite called Gaia, and
Mhm.
it measured the distances to a huge chunk of the stars in the Milky Way, and it helped us tell the difference between those two things. And so leveraging that is what let Matthias say, I'm not looking at galaxies, I'm just looking at nearby stars, and therefore I'm sure these things might be Dyson sphere candidates.
Interesting. So just to get into into the weeds of it, like, do you guys receive, well, how much data are we talking about here that the telescope receives? Like, what is like 1 hour of observations? Is that like a gigabyte of data, a petabyte of data?
Gosh, I should be able to do this in my head quickly, but I can't. Remember, when we do satellites, we have to get the data down.
Right.
And a big gripe I have with NASA is that it is not doing what it needs to do to get the data down from space.
The
So we have the
bandwidth.
Deep Space Network,
Hmm.
which is used for virtually all interplanetary missions that NASA does and for the James Webb Space Telescope, and it's completely saturated.
The
And
deep space
so
internet, basically.
it is, yes. It's very large radio telescopes, but it needs to be upgraded. When we launch missions like Kepler that looked for exoplanets and stuff, we left most of the data on board because we could only download specific portions that we could scientifically justify.
Oh.
And so NASA has been looking into optical comms as a way to dramatically increase the bandwidth.
Hmm.
It's challenging because, if it's cloudy on the ground, you can't use laser communication or something like that into space. And that would help a lot if we could get higher bandwidths. But no, the data we'd get down from space, like by modern big data standards, the rate is not very high just because we're limited by the Deep Space Network, unfortunately. But yeah, I can't tell you how large the WISE data set is, but I don't think we're talking about a petabyte by any means.
Does that mean you end up doing part of the computation filtering on board? Kind of, discard some, decide not to download some parts of the data?
Yeah, and you have to do some data reduction on board. So what WISE ultimately produces is a map. It's
Mm.
saying at this wavelength, when I was using this part of the camera or this filter, I took a picture with my, I've got pixels, and each pixel has this brightness associated with it. And that's what we get down. And my understanding is that they have to do most of the processing to get that good image on board. They can't. It depends on the mission. But they have to think very hard about downlink.
Right. And once you receive it, are you doing like Fourier transforms on it to, figure out where things are? Or,
It depends on the mission. So for WISE, it was an imaging mission,
Mhm.
and it took pictures, and then we stitched the pictures together. And there's a lot of calibration that has to happen. When you make a montage of lots of images, you have to get the balance right and adjust for things. These infrared detectors have a lot of funny artifacts that can be introduced. Like if it looks at a very bright star, those pixels will stay saturated for a while and not report faithful measurements for a little while, and you have to adjust for that. So there's a lot of post-processing that NASA does on the ground to make reliable images. And then once you have those images, my interest in it is to know how bright the sources are so that I can say, is it brighter at 10 microns at mid-infrared wavelengths than it should be? And fundamentally, all you're doing there is drawing a circle around your target and adding up all of the values of those pixels, and that's how bright the star is. Of course, there's a lot of data science that goes into calibration and error bars and all of that. But fundamentally for imaging, yeah, you're adding up the numbers.
So one of the questions I had is, and I think, people have supposed that if you had a Dyson sphere of some kind or a swarm, you could have outer layers which absorb the thermal
Yeah.
energy being
Yeah.
emitted from the inner layers.
A Matryoshka brain.
Yeah, you might not get the external emissions. And you have actually supposed that it might be better to run it hot because you actually use less mass. So can you explain the difference between those two
Sure.
viewpoints?
So the first point that people often get hung up on is that, well, an advanced species wouldn't waste any energy. You wouldn't have any waste heat. But, anyone who's had to think about thermal management of a data center knows that all the energy that goes in has to come out. You can't keep it. You'll melt everything. And so cooling is a major problem. And so being more efficient doesn't mean that you have less waste in this sense. Being more efficient means for every erg of energy that you send into the computer, you can do more calculations before you have to dump the heat. A major challenge of doing compute on orbit and building computers in space is that you cannot cool them except through radiation. The only thing you can do is put out radiators and let the heat radiate away. Because, you don't have a river nearby. You can't do water cooling. You can't blow fans across it. There's no air. That's the only way to cool it off. And so that turns out to be a really tight constraint on the temperature and the amount of compute you can do. It was interesting. I was trying to figure out what these numbers are, and I couldn't find a treatment of this in the literature that had been done properly. And so I did a paper on the theoretical limit for how many computations you can do. Like if you have a square meter of solar panel, what is the theoretical limit to the number of calculations you can do with that energy? But then, you have to radiate it all away. And so another idea is, well, don't waste that heat. Just put another computer farther out, catch that waste heat, and do a calculation with that. And to some degree, in some engineering scenarios, that's possible. But to first order, basically, if you're going to build an outer computer that's going to capture that waste heat, you might as well just get rid of the inner one and capture the sunlight directly. And just have one outer computer do the calculation. The inner one's just getting in the way and adding inefficiency for the most part. And so if what you're after is the most calculations you can do with starlight, then you kind of want to be as far away as possible because that gives you the biggest radiators and that lets you cool the most. And if you operate at lower temperatures, you're more thermodynamically efficient, but also you can do more calculations cold than hot and ultimate limits in what's called the Landauer limit of calculations. A colder computer can do more than a warmer computer. And so many people have argued that if there are species out there doing massive amounts of computation around stars, their computers will be as far away from the star as possible. And so that makes a kind of sense. There's just one problem, which is that if you're farther away to do the same number of calculations, you have to be much larger. Because as you get farther away, the starlight gets more dilute. And so you need bigger solar panels to get the same amount of energy. And that turns out to be where most of your mass is. It's in these collectors and in the radiators to get rid of your heat. And if you want to use a lot of energy from a star, you need a lot of mass. I mean, a lot of mass. So in Freeman Dyson's original calculation of, a swarm around the sun at about the same distance Earth is from the sun, he had to argue there was enough mass in the solar system to do this. And he did a rough calculation. And it's like, well, Jupiter has enough mass to do that. You could disassemble Jupiter and build a Dyson sphere. And in a later paper, well, it was actually a lecture that he gave, he worked out the details. Like, it's totally possible to disassemble a planet. And he outlined one way to do it. And he's like, if I can think of a way, the aliens can think of a better way. So it's certainly possible. But, the bigger the sphere, the more area it has. And so the more mass you need. And so if you want the sphere to be not, sort of room temperature, 300 Kelvin, but you want it to be 30 Kelvin so that you're a few percent more efficient in your calculations, because that's all you get, a few percent more, then you need not, one Jupiter of mass, but you need, I forget what it is, 1,000 Jupiters of mass or something like that. It's very large. It runs away from you extremely quickly, and it's strongly diminishing returns. So you need 1,000 or 10,000 more times the mass just to eke out a few more percent of calculation. And that strikes me as a bad trade-off. Like, I think they just go to another star, right? Rather than something like that. So I think the more practical constraint is to give up on that few percent of extra compute and just say, I don't have a lot of Jupiters of mass. I only have 1 Jupiter mass or less, and use that mass as efficiently as possible. So if you're mass constrained, you want to be as close to the star
Right.
as possible, because the same solar panel collects more light when you're closer to the star. And so I feel like being mass constrained will be where most species are. And so I actually expect the Dyson spheres to be as hot as possible if they're maximizing computation. If that's what they're after, I think these things will be room temperature or warmer.
Wow. Room
Yeah,
temperature or warmer.
I think you run them as hot as you can because you can do more calculations. The trade-off is, for a fixed amount of mass, you do way more calculations as close to the star as you can than you do farther away.
Right. So the limit being cooling becoming a strong enough constraint that you are forced to have a cooling plus mass, cooling plus the availability of mass.
It's both. It's energy. I mean, if you want to, it's energy collection and cooling. They go together. But the energy collection is a little more intuitive, right? That if I have solar panels and I have a light source, I want to get the solar panels to as efficiently as possible collect light. So I want them as close to the light source as possible, so that I, have as much energy as I can to do the calculations. That's fundamentally it.
So let's go the other way. Let's say they were not trying to maximize computation, but they were also have this other constraint that they're trying to minimize the visibility of their technosignature to other species, which could be a concern if they're concerned about hostile species, right?
So yeah.
How could they maximize output while still minimizing the footprint that they leave?
Yeah, it's very hard to hide the fact that you're using energy. I mean, if you're using a lot of it, you can't keep it. You got to get rid of it. And when you get rid of it, it'll be obvious. So some people have said, oh, they'll be super cold so that there's no infrared emission. The problem is then there's far infrared emission, and there's a huge amount of it, and it's super obvious. So you can say, okay, let's beam the emission away, and that's fine. You can do that, but you can't beam all of it away. And the stuff you beam away is generally not the waste heat you're getting rid of. So beaming can help a little, but you have to beam it somewhere no one will see it, and your efficiency goes way, way, way down. One thing we've been thinking about here at Penn State is how we could you use a black hole? Could you dump your waste heat into a black hole? So if there's a computer around a black hole, what do you get? And I think it might be possible. I think you might be able to hide yourself if you were around a black hole. There's a lot of other things to think about. But black holes will just eat up all of that waste heat, and off it goes, and it'll never shine. But, most species won't have a black hole around to do that.
Right.
So I think the bottom line is, if you don't want to be noticed, then you need to not use a ton of energy, basically. You want to use energy sparingly and not give yourself away. I mean, an analogy I use for this sometimes is, if you're walking down the street, you want to know who's home, right? You see all these houses and all the shades are drawn, all the lights are out, but you want to know who's home. You can put on infrared goggles and you'll see who's got the heat on. Like the houses that are warm on the inside, they're not perfectly insulated, and you can see the heat coming off of those houses. Okay, they're home, they're home, they're home. You see a bunch of computers, which ones are running jobs. You can just look, and the ones that are heating up are clearly the ones using the energy. So if you want to hide from infrared goggles, you just gotta turn the heat down.
Right on. So and how does this differ from radio telescopes, specifically the one in like Puerto Rico, the one that was made famous by the movie Contact?
Arecibo.
Arecibo, yeah.
R.I.P. Sadly, yeah. So this is a completely different approach from radio technosignature searches. There, we're generally relying on communication. So whether they're communicating with us specifically, trying to get our attention, or whether they're communicating with themselves and we just happen to be in the beam, like, we're behind one of the targets. Either way, we think it's probably pretty straightforward to distinguish radio photons, radio emissions that are generated technologically to convey information than it is from natural ones. The radio signals, because, if you're using it for communication, you need to be able to hear it and distinguish it, and not hear static, but hear the signal that you're trying to convey.
Right.
So on Earth, what we do is frequency compression. And this is great, obviously, for spectrum management and so on. But you say, I'm going to transmit at this one frequency or at this discrete set of frequencies. And all the information will be from the modulation of a signal at that narrow frequency. And that's great because then the receiver only has to tune into that small range of frequencies, just the bandwidth they're interested in.
Mm-hmm. Mm-hmm.
And all of the other radio signals and interference at other frequencies go away, and you can focus on what you're hearing.
Mm-hmm.
There are some other modulations and things and schemes that you can use, but at interstellar distances, if you're trying to communicate that really looks like the obvious optimal solution to the problem. And there are caveats about, sideband communication and what digital communication looks like and so on. But the point is, it's not going to look like a random radio source. And so radio telescopes, if they're outfitted with an appropriate spectrograph that can distinguish things at high resolution, can easily distinguish a technological radio signal from a natural radio source.
Mm-hmm.
That doesn't mean that if we hear something out there that's technological from an alien species, we'll be able to decode it. That's a totally different problem.
Mm-hmm.
But we will be able to say, I don't know what we're listening to. I don't know what it is, but I know it's not natural. It has to be technology. And so that's really powerful to me because communicating among the stars, we can talk about, future tech and alien tech and how they might do it. But everything we know about basic physics says that photons are by far the best way to do that communication in terms of efficiency, energy per bit, the fidelity of the information across space, and your ability to localize the source. If there's interstellar communications out there, I think it's definitely with light. I think radio is a great way to do it. It could also be optical comms, since after all, we're moving that way with NASA and so on. It could also be optical or infrared radiation. But we have surveys, I say we, the SETI community has surveys to do both kinds of searches.
Right on. Let me go back to one of the things you said about dismantling Jupiter. So let's
Yeah.
we have to talk about that.
Yeah. All right. I'm
So-
not
so let's-
advocating for that, by the way, just to be clear.
Let's say we're on Earth right now. Kardashev Type 1 civilization, would basically use all of the energy on its home planet.
Oh,
And-
a type 1 would. Yeah.
Yeah, Type 1. And let's say you, at some point, as we start to get there, we start looking at alternative sources and, the natural source being our star. How much mass would it take to, let's say, get to 10% of energy's output? Not like the whole.
No, I get I know what you mean. Yeah.
At what point does it become like, hey, maybe
Yeah.
we should start looking at the sun? Yeah.
Sure. Well, I think immediately, we're on Kardashev's scale or Sagan's version of it, something like a 0.72 or something like that.
Mm-hmm.
And, we keep adding all of this solar capacity, which is, giving us great energy supply. We have limited things like coal, but it's clear that renewables like solar and wind, I think, are, how we can increase our capacity without destroying our biosphere. But you can't get much higher than we are. If we have 10% the energy supply we have now, that becomes a major, ecological, or it changes the energy balance of the biosphere. We know global warming, that's a little different. That's from the carbon dioxide, and that's changing the energy balance in a different way.
Yeah.
But once we get to the point where we're, using like 10% the energy supply now, we're either adding a lot of heat directly to the atmosphere if we're using nuclear and coal and stuff like that, or we're covering so much of the planet's surface that we're changing the energy balance that way.
Yeah.
So if we really are going to say we're going to spend 10 times as much energy on compute as we do now, or 100 times as much, the only solution, I think, is to get it out of the biosphere.
Oh, wow.
And so I think it would have to be out there. So once you do that, the sun puts out 10 billion times more energy than hits the Earth. And so suddenly you've got all this energy that's just uselessly streaming out into space, and it's just there for the taking, and there's no negative consequence. There's no ecological feedback to collecting it in space. The issue is you've got to get the mass to do that out there in space.
Right. I often quote 1 megawatt of solar panels requires 5.5 tons of copper, which is, takes, and I always point out there's not enough copper on Earth to get to 10 times the amount of solar panels that we have right now. It's
There
just
you go.
Yeah.
Yeah. And I don't know if you need copper to make solar panels. I mean, maybe there's other ways to do it. I mean, the nice thing about a lot of these technologies is they're based on silicon. Like most of the atoms are silicon. And that's great because that's really abundant. That's everywhere. There's plenty of silicon. But yeah, the way we make them today, we assume you have all the copper you need. And there's not a lot of copper in space. Are you going to launch it off the Earth? And like you say, maybe there's not even enough of that. But even assuming we overcome that, you still need the mass up there in space.
Yeah.
And to get it there, you need to get it out of the gravity well. And
Right.
so, Earth has a pretty deep gravity well. It's very
Right, that's right.
expensive,
Mhm.
even with Starship or something. I mean, fundamentally, it takes energy to get stuff out of a gravity well. And you can't get around that, in that fundamental limit that you have to spend the energy to do that.
Right.
So I don't know. I mean, 10% of the light coming off of the sun probably requires something like the mass of Jupiter. I mean, most of the mass in the solar system is in Jupiter. I guess you could go to Saturn, but I don't think Mars is enough.
Oh, wow. Oh, wow.
So when we talk about building a Dyson sphere that collects more than what might be a trivial fraction of starlight,
Mhm.
we're talking about, projects that are far, far beyond anything that humanity will see.
Right. Right. We're talking about the apex of civilization kind of,
Well, I
project.
mean, yeah, and it's huge. Also, at that point, you are changing the environment of the Earth.
Yeah, exactly.
Because if that much sunlight is being collected and not streaming into space, you'll notice on Earth, like if the Dyson sphere is interior to Earth, then it'll start blocking starlight. Like that swarm will start blocking it. So, okay, maybe you can negotiate so that at only 10%, it never blocks the Earth. Maybe Earth is okay then. If it's exterior to Earth, then the night sky isn't completely black anymore. We're looking at the inside of this Dyson sphere, which means the Earth cannot cool quite as well, and that'll start to affect it. And certainly if you start talking about 50 or 100% of starlight at that point, the Earth's biosphere does not survive. So I do not advocate for us building a Dyson sphere around the sun because, I like the Earth and the things that live on it.
Right. So it may be. So let's say we were not looking at 10% of the sun's output, but 10% of the Earth's current energy usage, a much smaller amount.
You mean our current energy supply, or 10% of the sunlight that hits the Earth?
10% of the sunlight that hits the Earth.
Okay. Yeah.
So not to look at like 10% of the sun's output, which is enormous, right? But 10% of just the sunlight. Because let's say we start running out of, land within the next like 4, 5, 10 years. At that point, how much mass would we need to run it hot? To use the minimum amount of mass, you run it hot, you have it close in.
I don't have that number for you, I'm afraid, but it's not going to be that much. I would have to run that calculation. I imagine the asteroid belt might have enough to do that because that's a tiny fraction of the sun's total output.
Right. I'm wondering at what point people start making plans.
Well, I mean, it's the equivalent of 10% the surface area of the Earth.
Yeah.
Right. And so you need they're very thin. And so, that's not that much mass. I would imagine that that's completely mineable given the materials that are already in space. And it doesn't cost that much energy because you don't need to take it out of a planet's gravity well. You could take it off the back of the moon, or you could take it off the asteroids.
Right.
Yeah, I think that's doable.
Yeah. Because I don't think any species starts out wanting to build an enormous Dyson sphere that kills off its own biosphere. But these things probably start off with small incremental steps that,
No, I think that's a really important point that people often miss about Dyson spheres, that they imagine it has to be this like many millions of years massively engineered project. And, if you're trying to build a giant shell, which is impossible, it would have to be.
Yeah.
But no, I think just like our cities and all of the other very large projects we do that are generational, they kind of go up organically. There's no, nothing that prevents someone from launching or creating a data center out there in space somewhere. And as long as it doesn't hit the other ones, it's fine. And space is huge. They're not going to really hit each other if they're orbiting the sun. So, it's just, why not build another one? Why not build another one? And just like low Earth orbit is starting to get very crowded, at some point you'll start to run into a problem and realize you need to coordinate. But even then, it doesn't have to be a grand engineering scheme. So Yeah, Freeman Dyson said that he imagined that these things would arise kind of organically. It's just, why not launch one more, and the next thing you know it, you're looking at the ecological impacts.
Right, right. Let's say, what would be the first steps to kind of obtain mass outside of Earth? We've talked about the back of the moon, asteroid belt.
Yeah.
What are the steps that we need to do to get there? Like,
Yeah. I'm not an expert at asteroid mining and things like that. I've heard neat proposals. I mean, asteroids have very shallow gravity wells. And so if you can get stuff out there onto the asteroid belt, presumably you can mine it. There's a neat option on the moon, which is you could build an elevator. Like if you really want to mine the moon and move huge amounts off without rockets, there's this idea of a space elevator. And
Right.
it would, literally just lift things off the surface of the planet. It's energetically very efficient. It's unclear if any material that we could make is strong enough to build a space elevator off of the Earth. But my understanding is a space elevator on the moon or Mars is actually, in principle possible. So I could imagine that in a few hundred years, we're building a space elevator that can move serious amounts of mass up and down from the moon and Mars. But I think for what we're talking about now, the asteroids probably have plenty of mass. And there I'm not sure.
We talk about mass kind of generally, but in order to build things, you often need like specific elements like copper, etc. How does that break down? Like, can you deconstruct the mass and kind of reuse it as you please, or are we really looking for certain elements in there, or how does that
Yeah,
work?
the asteroids, for the most part, have all the elements we find terrestrially, and some
Mm.
elements that are very rare in the Earth's crust can be very abundant in the asteroids. The way the Earth formed, many elements ended up in Earth's core. They're called
Oh,
siderophilic elements. And so
uh-huh.
when the Earth was young, after the moon forming impact and when it was forming, things got kind of mixed up. And those elements that like to be in iron sank to the core, and the crust is very depleted in iron and any element that dissolves in liquid iron.
Wow.
And so most of the elements we have on the surface are there for other reasons. And a lot of them are actually from the meteorite impacts, from asteroids over the last 4 billion years that have struck the Earth and left elements that, all sank to the core when it was formed. So a lot of the stuff we need and think of as rare might actually be quite abundant in the asteroid belt. But I don't know specifically. I mean, it also depends, you work with what you have. If things are so rare you can't use them, you find a substitute. So I'm sure the people that have thought about asteroid mining and building things in space have thought about what elements you really need and what's abundant and what you can work. One thing about asteroid mining that's always made me kind of nervous is people talk about mining those elements and bringing them back to Earth. And it's hard to bring mass back to Earth safely.
You fire it off as a bullet and it lands like a nuclear, like an ICBM.
Yeah. Well, I mean, the atmosphere will always try to slow it down on the way in.
Yeah.
But the safest way to do it is with a rocket. And,
Right.
that's just like lifting mass.
Yeah.
And so if you have huge amounts of mass you're mining in the asteroid belt, I think it needs to stay up there. But, if you're building data centers in space, that's where you should probably keep it anyway. But again, I'm not an expert in this asteroid mining stuff.
Yeah, well, economically, if it takes money to get stuff off Earth, you want to keep it off Earth as long as possible, right? If the
Yeah,
gravity well,
make use of it.
gravity
Yeah.
getting out of the gravity well is expensive. So, yeah, let's say it strikes me that a species that kind of grew up on an asteroid belt would kind of look at us and say, like, "Wow, those guys are very industrially poor." In the sense that we don't have a lot of elements compared to, if a species that
Oh,
is on a belt, they would have a much more industrial society because they would have just more industrial metals to start off with, more of a resource endowment, from the get-go rather than
huh. So you're imagining a species that evolved and, first developed technology on asteroids.
on asteroids. They
Huh.
would just start off with this abundance of, resources.
I'm not
Um,
sure. We talk about the origins of life in the universe, and I'm not sure I've heard that suggestion. Now, large asteroids like Vesta and Ceres can have substantial amounts of ice. I think people have sort of speculated, maybe even microbes or something. But the idea of like a biosphere, a rich biosphere with animals and things on asteroids is kind of new to me. I think we generally imagine it needs to happen on or near the surface of a pretty large body, like a planet or a moon. And let me see, is it true that in general, yeah, we generally imagine it'll happen on a body where it has composition on the surface similar to Earth. But I mean, when we find really rare elements that are super useful, like lithium, we're pretty good at, mining it and getting it out. Lithium's super important for us, but it's also very, very rare on the Earth, as a lot of elements go. So, yeah, I don't know. I mean, if it's valuable enough, like gold or something, then you just make a point of being very efficient at not leaving any in the ground.
Right. I often look at things as like technology trees. And a Dyson sphere is kind of the end point of a technology tree, but you need a bunch of things to happen before you kind of get there.
Yeah.
What do you think, like, if you look forward on a tech tree basis, what technologies do not exist today but would have to be invented in order to
Yeah.
get there? That
Yeah.
makes sense. Yeah.
Obviously you need space flight, so we can tick that one off.
Mm.
My guess is that the big one is the scale of what you're talking about is so large that I think you have to invoke exponential growth. You need some way to have a runaway exponential that mines so much material, builds so many things, that you don't need a person or an assembly line with actual people making every single component. So I think it's self-replicating machines, von Neumann machines, in the sense of like physical objects that can make more of themselves, that sense of the term. That I think is the only way I can imagine the ramping up the scale of, building solar panels, for instance, by whatever it's going to take, 13 orders of magnitude. That scale of thing is what I think is involved. And in a lot of these discussions about a species populating the galaxy or building a Dyson sphere or building lots of Dyson spheres, I think it was Frank Tipler that really pushed this idea that a self-replicating machine would just do it. Like as soon as you had built them and you set them off, then it's like bacteria or mold or viruses or something. They just, they self-replicate so quickly that they're just limited by the amount of material they have. And it doesn't take that many e-foldings before there's as many of them as you need to do anything to populate the whole galaxy. So there's no fundamental reason that, we can't build self-replicating machines. In some sense, biology, we are self-replicating machines, so we know it's possible. Self-repair is a big thing you have to worry about, and you have to worry about, drift, genetic drift that 5,000 generations down, they're still doing what you wanted them to do in the first place. That's quite a problem. There's questions about whether once you've done that, those things themselves are a form of life that deserves some kind of moral standing. And, if it's AI, then, there's your descendant species, right? It's a fascinating idea, but there's a lot there. But I think that's it. If you're serious about collecting vast amounts of solar energy, I suspect that's the big one. I mean, this is to say nothing of building things in space, right? I mean, how do you build a foundry on Ceres? How do you mine an asteroid? How do you smelt, and how do you build, microchips in space and all of that? I mean, there's a lot of questions there too.
Which we kind of gloss over, but we expect that, we could probably find other ways of building stuff without Earth gravity and,
Yeah. So a game that Freeman Dyson played a lot and I subscribe to is to distinguish what's physically possible from just engineering, right? If it's just engineering, it's just a question of how much it costs and how long it will take to figure it out. If it's physically impossible, then just put it away. Like,
Right.
I was hearing people talk about, we'll have a Dyson sphere in like 50 years or something. And that's a great example of something that is not just engineering. No matter how smart your AI is, no matter how clever you are, no matter how good your technology, it is literally impossible to build a Dyson sphere around the sun that quickly. Literally. Like, there's no way it can happen. And it's not that I'm not being imaginative. It's that there's not enough mass. Like, the mass is in Jupiter. And so you cannot get that much mass out of Jupiter in 50 years. Like, if you took all the energy the sun puts out for 50 years and with perfect efficiency used it to lift mass off of Jupiter, you would still not have enough time. And so it's not a question of technique. It's just a question of fundamental physics. It's not possible.
Just getting it out of the gravity well, You just don't
Right.
have,
And, it's not, oh, well, use rockets. Well, what's powering your rockets? Where are you getting all this energy? And there's no technological solution to there's literally not enough energy to get the mass out of Jupiter's gravity well in the solar system. So, and that's the game that Freeman Dyson played when he was talking about Dyson spheres and how to build them. He wanted to know if it was physically possible. So first, do the energetics allow it? Is there enough energy? Is there enough mass? Yes.
Yeah.
Second question, can you think of any engineering solution that in principle should work and the rest is details? So for lifting mass off of a planet, he had this clever idea that you could use its magnetic field like a handle to spin it up and then get it rotating so quickly that the energy cost of lifting stuff off of the surface would be very low. And then you could use a space elevator or even very low powered rockets and just lift things off the equator. So there you go. That's a way it was possible. And he would say, like, I'm not saying they would do it this way, but the fact that I can think of a way that's plausible is enough. They surely have a more sophisticated way of doing it, but it doesn't matter.
But that way even with that way, 50 years is not a possibility.
There's not enough energy. No.
There's not enough energy. Wow. So these ideas that, I've heard, this conversation started off with the guy that invented RLHF, reinforcement learning, human feedback, Paul Cristiano, making kind of a 15% chance of a Dyson sphere by 2030 and a 40% by 2040. And that was the starting point of this conversation. And I kind of want to know whether it was kind of physically possible or you needed what I call magic, which is like this magical thinking. And I guess the assessment is that even if you had a 50-year time frame, it's still not enough time. It's still not enough time.
No, it's not even close. And again, it's not, it's not that we can't figure out how to do it. So, the fastest you could imagine, I think, the total output of the sun could disassemble Jupiter in something like 100 years if it were all focused 100% only on that problem of disassembly.
Which you need a Dyson sphere to do because
you already need the Dyson sphere, right? And so, I suppose the scheme would be that you start building collectors that are entirely focused on disassembling Jupiter, and then the more mass you get, the faster you disassemble it, and so on. I haven't worked out how long that
recursive planet deconstruction,
right? And so I don't know what it's going to work out to, but it's definitely not 50 years. Now, it depends on what you mean by Dyson sphere.
Yeah,
I mean, if you mean you're collecting 10% of the sun's light, right, it's not going to happen, and you don't want to do that anyway because of the effects on the Earth. But if you mean we're just out there doing compute in space, then we've already got our tiny, puny little Dyson sphere. We've already got things in space collecting starlight and doing calculations with them and being habitats for us to live in and so on. So we have one. It's just a matter of degree. It's just these 13 orders of magnitude between what we're doing. No, more than that. Probably, 20 orders of magnitude between what we're already doing and what people are probably thinking of in terms of a Dyson sphere surrounding the sun.
Just to digress a little bit, besides a Dyson sphere, which is a primary kind of energy collector, are there any other kind of space megastructures that a species might start building or that have been proposed? I mean, I've heard people have proposed O'Neill cylinders and et cetera, but does anything else make sense or even have approach the kind of...
Yeah. I mean, I try to stay agnostic about this stuff. When I'm looking for aliens, I try not to be too specific. Like if they did exactly these things, then we could detect them because I don't know what aliens do. And I don't want to premise my search on a very specific, unlikely, contrived scenario.
Right.
Energy collection feels really fundamental to me. Like it's almost definitional in technology that you are collecting or manipulating energy. And so computation feels to me like, the more computation we have, the more uses we find for it. It's so fungible as a commodity and it's proving so versatile. And it seems to be very cheap to produce. We keep getting more and more efficient, approaching fundamental limits. That strikes me as universal. That does strike me as so useful that any species will discovers computation will have an unlimited appetite for it. And it requires energy, fundamentally. So I like computation in space as the most likely reason you'd see a lot of stuff. Habitats are another one. If you want to spread, you need a place to be. And so if a species, for whatever reason, is maximizing its numbers, its literal numbers, it needs surfaces for that. So the original idea of an artificial biosphere, I think, might be another reason. Those two have slightly different consequences for where you want to put things exactly. A biosphere is probably, you're going to optimize for whatever temperature of, your biology. And with computation, I think you optimize getting close. But, from my perspective, trying to find them, they're kind of the same. They should have the same signature, which is that they're taking what should be starlight that streams away at optical energies, absorbing it, doing whatever, and then dumping it out as infrared radiation.
In a way, biology is a form of computation anyway. So
Yeah, sure. Absolutely.
So let's say you find a signature. And I think this has happened before, I think with a Tabby star. Maybe you can explain what was Tabby star and what happened with that. Yeah.
Okay, yeah. So when I first started working on this, we were imagining that there might be very large single structures. So the way we've been talking about a Dyson swarm, the individual elements could be quite small, right? They could be the size of our current satellites, maybe even, the size of buildings or something like that. But on an astronomical scale, those are just dust particles. They're so small.
Right.
It's conceivable that there would be networks of them flying in formation, or even single large structures that are like planet-sized. That's about as big as you can get before self-gravity makes things really hard, planet-sized. And if there were networks like that, or meshes like that, or solid panels like that, and they pass in front of the star, which, I mean, from your perspective, they're always around the star, but if they happen to pass between Earth and the star, then we would notice the star getting significantly dimmer for a while. And by significantly, I mean like 1% of 1%, but we can do that now. And then, get brighter again when it went by, and it would look like a planet passing in front of the star. But if we tried to study that planet, find how massive it is, look at its atmosphere, do all the things we like to do with exoplanets, we'd find it to be a very strange planet. Why can't we measure its mass? Why does it seem to have a non-spherical shape? What's going on? And so I was just thinking about this because NASA's search for planets around other stars had produced so much data that we could say, well, if these things were out there, if there is a species that had filled the galaxy and surrounded it with these giant megastructures to do whatever, compute whatever, we would have seen them. So NASA had actually already shown us these things don't exist. And I was working on a paper that made this point when Tabby Boyajian, who was a postdoc at Yale at the time, but is now faculty at Louisiana State, she was talking about her science and everything in my office. And she said, I've got this very strange star. I've been asking everybody if they can help me figure out what's going on. And she showed me the data. And I'm like, this is exactly what I said NASA showed didn't exist. This is some star with giant Jupiter-sized things passing in front of it that are not round. And it just made no sense. And so, Tabby and I, working with the Breakthrough Listen Project, which is a giant SETI initiative run by Andrew Simeon and supported by Yuri Milner. The Breakthrough Listen Project was using the Green Bank telescope to look for radio signals. Well, let's take a look. Maybe they're communicating with each other. We can get their radio signals. And then the press got wind of it that we might have found alien megastructures, and it was on, Colbert, and it was on Saturday Night Live, and it was a very strange experience. But Tabby was very shrewd, and she started to Kickstarter to raise money to do the research to see, what it was. And so we rented time on a private telescope network at Los Cumbres Observatories. And we monitored it. And the next time one of these giant things passed in front of the star, we made lots of measurements at different optical wavelengths to try and establish if it was a solid opaque object. And what we showed is that it was definitely not a solid opaque object. It was totally characteristic of astrophysical dust, which is just everywhere. It's our big confounder. And so whatever it is, it's dusty and it's not opaque. And there's no reason to think that technology would look exactly like dust. And so that has helped us put that speculation away with Tabby star. And we've never found another star quite like it. It's still weird and an enigma. Tabby's original idea is that it's giant swarms of giant comets. That's a weird thing. We've never seen or hypothesized those before, but it does seem to explain the data. And so Tabby and I are both part of a large team using the James Webb Space Telescope to try and find the infrared emission from these comets. And so I'm hopeful that that will bear fruit soon and we'll finally solve the puzzle of Tabby's star.
What does your decision tree look like from the first kind of infrared observation that, of a potential interesting technosignature? What does the decision tree look like, until confirmation? What are the steps that you would take?
So the first thing you do is you ask, what sort of object would naturally have that kind of emission?
Mhm.
And with galaxies especially, we expect them to have that kind of emission. And for young stars, we expect them to have that kind of emission. And so it's behaving totally like an ordinary class of object that you've seen many times before. There's no reason to invoke aliens. It's clearly just another member of that class. And sure, we could be wrong, but what are you going to do, right? It looks just like nature. Then you've got a few, like Matthias's 6 stars that he found that don't seem to make sense. And so now you've got to look more carefully. And fortunately, we have a lot of tools in our arsenal to study these things because we want to know at what wavelengths exactly is it bright in the infrared. And so we do spectroscopy at that point. We look more carefully at 10 microns and 10.1 microns and 10.2 microns. And we look for the telltale features of dust or other of elements that we associate with certain things. So we're like, could it be this kind of object, this kind of object? So for instance, for 2 of Matthias's objects, it's pretty clear now that what's happening is that behind the star in the distant universe, the star is kind of photobombing our attempts to image a distant, very dusty, very infrared bright galaxy.
Right.
So these things are pretty rare, but some galaxies have so much dust that you can barely tell there are any stars there. It's just glowing dust. And we basically understand why they exist. It's not a huge surprise they exist, but they're way out there in the distant universe. And at least 2 of his stars have just passed directly in front of one of those galaxies from our perspective. So we see the optical light from the star and say, oh, it's a star. And then we see the infrared emission from the galaxy behind it. And we're like, where is it coming from? And so in 2 cases, it's pretty clear that's exactly what's going on. Maybe all 6 cases, although that seems too many for chance. So that's the kind of thing. You check to make sure that you're looking that you're really looking at just one object and not many objects. And it turns out that's the dominant false positive, is that we get a blended source. And that's one reason we used WISE and not the earlier missions, is that it had the image quality to generally rule most of those out. But yeah, there's always going to be a few.
Let's talk about like Starship. So, SpaceX is doing Starship. The expectation is for cost of launch to go down 90%, maybe even 99%. How would the makeup of telescopes outside Earth change if you had this ability to lift so much more mass? If you could have a telescope at the same price, which was 10 times more mass, how would that change the work that you do?
Yeah, I mean, it could be profound. I'm very excited at that prospect. I have found that the astronomical community is kind of split on this. We spend a huge amount of effort reducing the mass of our telescopes. For instance, to give you a sense, the James Webb Space Telescope costs like $10 billion to launch. And one reason it was so expensive is because it was very hard to understand how to build a mirror that size that we could launch into space. Because it's over 6 meters across. And so they just looked like, what is literally the lightest material we could make these cryogenic mirrors out of? And so it was like, well, it's going to be, beryllium. I was like, all right, well, what would that take? It's like, well, it would take the largest amount of pure beryllium anyone's ever made, and it's toxic. So we would need, it was just ridiculous. I'm like, all right, well, you got to do what you got to do. And so they made all of these segments out of beryllium. So that kind of calculation goes away if you don't need the world's lightest mirror and you don't need to do them in segments that align, and you can just launch a monolith. Another benefit is right now it's got to work. Like one of the reasons JWST costs so much is it has to work at that price.
Redundancies and
right. And a lot of the components cannot be redundant. Like you can't have a second primary mirror.
Oh, wow.
Right. There's a lot of single points of failure. And so when you add up all the single points of failure, each of them has to have like a 10-year chance of failure with a lot of zeros. right?
Yeah.
That's a many nines of reliability on everything. You have to prove it before you launch.
Right.
That's very expensive. But
Hmm.
if launch is so cheap that you're like, the way that I'll get all my nines is I'll just launch 5 of them. And if 2 of them fail, I don't care. So if that's an engineering optimum for the problem, then maybe that's what you do. Or instead of having, an instrument suite of 4 instruments on JWST, you launch 4 JWSTs each with 1 instrument. Maybe that's an optimum that's better. So it really opens up the space. It opens up all the things you can do.
Hmm.
And so I'm excited that it's possible the next JWST functional thing won't cost 10 billion, it'll cost 1 billion for those reasons.
Right.
Now, other people at NASA are extremely skeptical, and they say most of the cost here is not mass reduction. It really is it's the reliability. It's just where every instrument is bespoke. We're building a brand new one. And it's the person power that goes into planning a mission of that complexity that's actually where most of the cost is. So I'm sure Starship will change the engineering optima. It will open up a lot of new vistas, but I don't know if it's we get 10 times as much science for the dollar, or if it's we get 30% more science. I don't know. I hear different arguments from NASA. But that said, I think if Starship is so reliable that we're willing to put $1 billion on it, then yeah, I think there are things that we never dreamed we could put up there that we'll put up there. I'm sure it'll be. My bet is we get many times as much science, not 30% more or something.
So typically, I think when you have budgets get allocated to the highest priority thing, and the lower priority things kind of get bounced for many, many years without actually progressing up. Like which are the, I think, kind of things which are not on NASA's priority list right now, which might get done with lower launch cost?
So it's very hard to predict how NASA's going to fund science. They are not about optimizing science per dollar. That is not how NASA functions. And I mean, I've had NASA administrators tell me NASA stands for not a science agency. NASA's purpose, it has a lot of functions, a lot of things, and a small fraction of what it does is science. And that's its public facing. That's what most people think of NASA, right? It's astronauts and it's science. It's Hubble, it's JWST. And so because it's public facing, NASA needs to maintain it because, NASA is one of the most popular government agencies, not just in the US, but in the world, right? You see people with NASA logos all over the world because it's just such an inspirational agency.
Yeah.
And that's because of the astronauts and it's because of the science it does.
Yeah.
And so we advise science on NASA on what the important science is. It looks at that and says, okay, but what can only be done in space? If it could be done from the ground, they're like, that's National Science Foundation. Like, we don't build ground telescopes. They do. But the point is that if we say this science, could be done much cheaper on the ground, they say, well, then we're not interested. They're not optimizing the science return because they're not foundationally a science agency. So it's hard for me to really understand what will happen. That said, NASA does listen to us about what's important, and we think about what can we do from space we cannot do from the ground. And the answer generally is you don't want to do radio in space because radio waves penetrate the atmosphere. Do it on the ground. It's cheaper. Optical astronomy, there are advantages to going to space. Hubble shows that. But in general, NASA is going to look at gamma rays, X-rays, ultraviolet, mid-infrared, far infrared. These are the wavelengths that you cannot do from the ground. And so, we have ultraviolet telescopes in space, and they're some of the most scientifically productive instruments in the world because it's the only way to do that science. And there's amazing things that happen at all of those wavelengths that you can't access in any other way. So generally speaking, it's the kind of science that you can do at those wavelengths. And so I'm very hopeful, for instance, that we will get a far infrared mission that will look not at 10 and 20 microns, but out at like 100 microns. It's been a long time since we've had an instrument that could look at big swaths of the sky at those wavelengths. And so I'm excited that we might get an all sky map at 100 microns or something like that. And, if that instrument could be not this big, which is kind of what they're talking about, but have an 8-meter mirror, that would just be astonishing what it would open. So I'm just making this up, but that's generally how I think about NASA science.
Indeed. How about the moon? NASA is on the, planning on moon missions, and there's been various talks about building a base on the moon, even human habitation.
Yeah.
How would putting a telescope on the moon, would that be beneficial? Where would you put it?
Yeah.
And, what would the major differences be?
I think a lot of people are extremely excited about the possibility of telescopes on the moon.
Mm-hmm.
I say radio waves penetrate the Earth's atmosphere, so you don't put radio telescopes in space. But we use radio all the time on Earth for our technology, and that causes a huge problem for radio telescopes. In general, they can, use dishes to kind of block out stuff on the ground and just focus on what's coming from the sky. But stuff still leaks in, and it contaminates everything we do. And these satellite constellations are just destroying our ability to do radio astronomy, because these satellites come by, and even if they're not sending a signal down to Earth at that frequency, just their electronics are noisy. And our telescopes are so sensitive that these things are incredibly bright at radio wavelengths. So there is an argument for going into space. Now, there's still radio interference in space because our radio waves go out.
Yeah.
But if you just go to the far side of the moon,
Mm-hmm.
the moon acts as a shield, and there's no radio frequency interference.
Right.
Putting a radio telescope on the far side of the moon would be amazing. And there is a NASA mission actually that's done this for the first time, just to kind of try it out. Infrastructure on the far side of the moon is very hard because you can't communicate with Earth. And
it will also be low energy, right? Because you wouldn't get, or would you still get sunlight?
Sure, yeah, you still get the same amount of sunlight. Yeah, the sunlight's not such a problem. I mean, it is a problem in the sense that for 14 days, there's no sunlight.
Right.
So you need a lot of batteries.
Yeah.
And so that's a lot of mass. And you need a way to communicate back. But in principle, it's just amazing for radio astronomy. Now, the problem is, as soon as you say, all right, we want to build something on the far side of the moon, everyone's like, great, let's build the infrastructure to build your stuff. And then they start putting orbiters around the moon. And they set up all this wireless communication across the moon. And you're like, that defeats the entire purpose of what we're trying to do.
Oh my gosh.
And then they're like, oh, we'll shield them and we'll turn them off when they're on the back side. And we're like, you have no idea how sensitive these telescopes are. It's just like if you go to Green Bank, West Virginia, to the National Radio Astronomical Observatories there, it's a radio quiet zone, and you're not allowed to have anything that transmits wirelessly. And if you get close enough to the telescope, you're not even allowed to have airplane mode on your phone. It has to be completely powered down. And now, because of the way that, these technologies work to find your phone if it gets stolen, even a powered down phone is too loud. And, they say the reason you have to turn your cell phone off is we can detect it with our radio telescopes. We could detect it if it were on Mars. Like, we could pick it up. So a lot of us are hopeful that we'll get a radio telescope on the moon. It would be great for SETI. It would be great for studying the distant universe and how the universe formed. There's so much we could do with it. There are proposals to try and protect the farthest reaches of the moon from any radio signals. The idea is that if you're going to put things in orbit around the moon, you don't put them in orbit so they'll ever go over that area. You keep that side completely protected. For astronomy and stuff. But my guess is that the economics of going to the moon are going to just completely dwarf. Like, people will just do what they do. The same way that Starlink went up and just completely wrecked all of our plans for astronomy. We have the Rubin Observatory, which is going to make a map of the southern sky every 3 days. Like, the data volumes are incredible. We've been planning for this for over a decade. We've put $1 billion into this amazing observatory. And now every time it takes a picture, it gets Starlinked. That's what we call it. Big old streaks through every image. And people are like, oh, just take them out. You can edit them. But we're not making pretty pictures, and we're just trying to get the streaks out, right? We need to know what was there. AI can't tell us what was behind the streak because it's a streak and that's what we saw. And so it's probably not going to cripple the mission. We've reworked, but now we're putting all this work into it. And the same with Starlink and the radio. And so my cynical guess is that the rush to the moon, people just won't think about all of the amazing scientific opportunities that are available. and they'll wreck it. It's similar to Mars. Like, we really want to study whether Mars might have ever had life. It looks like it had water. A lot of people have strong expectations at one point it hosted life.
Yeah.
It's conceivable that there are bacteria living in the soil, just a little bit down still.
Yeah. Yeah.
Totally plausible. But as soon as people go to Mars, we will contaminate it.
Right.
And the sensitivity of our life detection experiments, as soon as people go there, it'll be, more people, right? And, we shed skin cells, we have poop, we have all this stuff that we leave on Mars. There's a windstorm, and now it's everywhere. And it's going to make trying to study life on Mars very hard. So we kind of got to hurry up and do all of our life detection experiments before boots hit the ground there. And yeah.
One of the things that I wanted to ask is, do you like in the machine learning AI space, we see Chinese researchers are now kind of 50% of top papers. In astronomy, do you see that? Do you see this emergence in the last decade of research coming out of China? Not just collaborations like with the European Space Agency, but your research which was kind of originated in China and ideated in China and being published in international kind of fora.
Yeah, definitely. It's on the way up. I mean, the American Astronomical Society has journals, and they've seen a very large increase in the number of Chinese authors in our journals, which are sort of the premier astronomy journals in the world. There's also a European one, Astronomy and Astrophysics, but we've seen a big increase in that. Also, in radio astronomy, China has built this incredible 500-meter radio telescope that's more sensitive than Arecibo was. And so they've kind of taken over that aspect of things. And yeah, they've collaborated a lot with American radio astronomers to understand, how best to use this new instrument. So yes, I think the Chinese sciences in astronomy and astrophysics and space sciences and radio astronomy definitely seem to be on the way up, for sure. And it's great. I mean, it's fantastic. We just had a conference here where we invited some Chinese astronomers to come tell us what they're doing. And yeah, it's been amazing.
How do you judge the quality of the research coming out? Is it on par with the quality in the US? Is it,
A lot of it's not in my field, so I wouldn't want to say or try and judge it overall, but I don't have any reason to think that it's subpar.
I see. Very good. Going back to the Starlink again, after the first Starlinks went up, in the kind of astronomy groups, they complained about the streaks. The Starlink team said that they did some stuff to reduce the amount, reduce the amount of reflected light, et cetera, et cetera. Did that really work, or did that help?
It helps. It makes them a little dimmer. I mean, we still see them because these telescopes are so sensitive. Yeah. I mean, they're saying, oh, well, they're in shadow. They're not reflecting any sunlight. It's like, well, there's still moonlight. There's still light off the Earth. We can still see them there. But it definitely helps. We appreciate the effort. Every bit helps. But yeah, we wish we had seen this earlier, and the first ones that went up had been painted blacker, and that this had been, that shielding their electronics better and keeping these things darker had been a priority at the beginning. Because I don't think it really affects Starlink that much to have them painted black or to have shielded. I mean, if these had been engineering constraints at the beginning, I don't think it really would have slowed them down. And so, right, especially thinking about the moon, I'm hopeful that, they'll consult us first and just see what they need to do so that they don't ruin astronomy when they go to the moon.
What happens? I mean, there are plans, I think, over the next decade to put up 100,000, multiple, 10,000, 20,000 mini satellites. Starlink has a plan. Amazon has a plan. How is that going to affect astronomy?
It just makes it worse. It makes it really hard. I mean, these are giant, $100 billion industries and stuff. The cynic in me says there's no way that, us astronomers are going to be able to stop it or change it in an important way. I hope they listen to us, though. I'm more worried, though, that that's just not sustainable. And, this gets back to just engineering versus just basic physics. The number of objects you have in orbit, it's getting problematic. And you can't, they're constantly dodging debris right now.
Yeah.
I worry a lot about Kessler syndrome. We don't know at what point it becomes, I mean, there's the idea that they all just shred themselves to pieces on their own dust and you can't put anything in orbit. Okay, that's like terrible endpoint. But even before you get there, I don't know how sustainable the traffic is going to get. When you have derelict things, when you've got, little pieces that you don't know about. Yeah, I just worry that it's not sustainable that way. But also, it's going to totally change the night sky to have these things up there all of the time. I don't know, it sounds corny, but I think that the sky it's part of, human heritage, the whole earth, it belongs to all of us.
Yeah.
And just like polluting the atmosphere is something that affects all of us and we should all get a say in, I think the night sky and what it looks like I think it needs to be more of a conversation with everybody. We shouldn't just see it as having no negative impact to put all of these things up there. So I don't know. Organizing humans to agree on how to treat these commons and protect our environment like that is not something we've historically been good at. And I imagine that once they plan to put 20,000 satellites up there, they're willing to talk and say nice things, but they're not going to say, all right, maybe we don't. So, yeah.
Speaking about international cooperation, there's a lot of like treaties. There's some treaties on who gets to land on the moon or who gets to, that the moon is not a space that you can declare your own space, et cetera, et cetera. There's all of these treaties that people have come up with. Do they actually hold any weight, or is it kind of just airy kind of?
Yeah. Again, I'm not a space lawyer. Zach and Kelly Weinersmith have a nice book, A City on Mars, where they look at a lot of these issues. And I know it made a lot of people mad, but I learned a lot from that book about space law and what it can do and it can't do. And I mean, I think we saw with the Artemis Accords that as soon as treaties are getting in the way of what countries want to do and what companies want to do, we renegotiate them. I mean, that's how law works, right? And the Outer Space Treaty and the Moon Treaty are so out of date and just did not contemplate so much of what's going on that they kind of need to be renegotiated. And they are, like with the Artemis Accords. I don't know. International law is actually an example of where humans do get together and make agreements about these things.
Right.
And yeah, it's up to our people and our governments to make sure that we enforce the things that we all agree on. I don't know what's going to happen in space. I'm personally very skeptical about the financial return of putting huge amounts of mass in space, asteroid mining. I mean, it's very cool and I want to see it happen, but it's hard for me to believe that it will be profitable to anyone. So, and I'm willing to be wrong. That's just my guess. So I'm hopeful that in the end it will be governmental, and that because it's governments doing these things, that they'll be willing to, respect treaties and come up with treaties that make sense for the entirely peaceful and cooperative use of the moon and Mars and asteroids. And we have a great example in Antarctica. Antarctica, no one's fighting wars over Antarctica. It's a commons that we all can enjoy for scientific purposes and tourism even. And everything about Antarctica is better than space. It's a better place to live by far.
Right.
It's much easier to get to. It's much easier to build things there. It doesn't get as much sunlight, and glaciers aren't great places to build things. Other than that, like everything about it's easier and better than space.
Right.
And so some of the things people are like, let's go do it in space. It's like, well, do it in Antarctica first. Prove to me that. That's easier. It's better. You'll make more money. If you're not doing it there, why are you doing it in space? Because it's cool. Great. I like that it's cool. But so it gives me hope thinking about Antarctica that maybe we can treat space the way we've treated Antarctica, which hasn't been perfect, but, has basically worked for decades.
Indeed. So we see a lot of graduate students in physics who have moved over to machine learning and data science.
Yeah.
So have you noticed that in your graduate student group as they graduate? Yeah.
Absolutely. Absolutely. I mean, all the graduate students are thinking about how they can apply machine learning to our data science problems. I haven't learned a lot of it myself, but I know the basics, and I have a postdoc that's, helping grad students work on this stuff. And yeah, I mean, our data sets are so large and the problems we want to solve are all novel. Like we don't have a lot of standard software packages that do standard analysis. Every instrument we build is entirely new kind of data product, and we're always trying to work at the cutting edge. And machine learning can help in so many ways to do those things. So yeah, we try to import all of the mature, portable machine learning techniques that are relevant to what we do into astronomy. We have a whole institute here at Penn State for computational and data sciences that has people that are trained in those techniques that help, us old-fashioned researchers that know the old way of doing things make the transition and do the best science we can. So yeah, we're very grateful for all of the hardware and software developments in machine learning that are letting us do great science.
Which of the things have been ported over? Are you using a large amount of GPUs? Are you running neural networks? A lot of neural networks don't work that well for numeric data or tabular data in general. So, what techniques have been ported over?
Well, yes to all of those. We have a supercomputing center called ROAR, which has, gives you the options of using, all these different kinds of cores. And I'm not an expert here, but my sense is we tend to use, we definitely use neural networks. We build emulators. I'm not an expert, and I don't have at the tip of my tongue all of the methods we're using. But my sense is that when a expert in data science sees what we're using, we're like, oh, those are like 5-year-old techniques. Right? These are behind the times. And we're actually like, that's good because it means they're well understood, they're well documented, like, people have figured out their limitations. And so we know how to use them reliably. So yeah, I'm okay that we're always a little behind the curve on these things because we need to understand the limitations of these tools so that we can make confident inferences about what their limitations are.
Right on. When you look at the field, what are the three kind of major like scientific problems that you see in the next 5 years, and what would be a pathway to kind of figuring those out? What do you think are the three major things that you might think about as very important research directions to follow?
So my approach to science is, if you build new infrastructure, scientific infrastructure, new observatories, new all-sky surveys, you collect vast amounts of data. That opens up science questions you didn't know you wanted to answer. Astronomy is very, it's very blue sky. It's very unapplied. And we have the problems we really want to solve, like we want to find an Earth-like planet and measure its atmospheric composition. And, those are great goals. They're very challenging to accomplish. But the instruments we build to do those things and the instruments we build to do other things will also bring up whole new things that we can go explore. So for me, it's how do we take new all-sky maps? How do we collect vast amounts of data across the whole sky? And then how do we access those data, in a useful way? The Rubin Observatory will collect petabytes of data. And when they built it, there was not when they conceived it and drew it up, they had to rely on Moore's law because there was no way to move that much data off of a Chilean mountaintop at the time. It was impossible. And there was no way to analyze that much data. Normally, the way that these things work is, you ask for some data or you're interested in some object and you go and you download the data and you put it on your laptop and you manipulate the data and stuff. But these data sets are so vast that we are having to learn to submit jobs to supercomputers to filter through stuff and figure out what we need and to actually do our science over there. And we need experts in data science that, can teach us about the custom SQL language that they have built for this data set that only astronomers use. And we have to learn to do that. So it's not so much a specific scientific question that needs a specific tool. It's that we need to get better as a scientific community at understanding how to manipulate well-standardized data at petabyte scales and get what we need out of it. Myself, I like problems I can do on my laptop, right? If my laptop's getting hot, I'm like, I need to optimize this code. I like little projects, single objects, and things like that when I'm working myself. But to find that slice of the data that's relevant to me, I need to understand better how to do petascale computing. And that requires what we've had, but we need more of, is this intermediate layer of people that speak astronomer, but know the data science and can, sit at that interface. So there's a lot of opportunities that have been presented for these sorts of collaborations. Microsoft is great about this, recognizing that astronomical data sets are some of the largest data sets in the world. They're completely public and open.
Yeah.
There's no personal identifying information. I mean, it's it's pure open research. And so they're great test beds for new technologies. And so I've been very heartened to see all of the industry academic to use these data sets as test beds and help us do science. We're very lucky that we have that. But yeah, we're producing a lot of data now.
Amazing. Professor Wright, thank you for your time.
My pleasure.
It has been an amazing and very informative conversation. And I definitely look forward to, more discoveries as the map gets more defined and with greater resolution.
Yes, me too. It's been great being on. Thanks for having me. This has been a lot of fun.
Thank you. Thank you so much. And bye-bye.
Bye-bye.
I hope you enjoyed that delightful conversation, and I hope you join us on the next episode. You can subscribe to Emergent Behavior on Spotify, YouTube, or Apple Podcasts. You can find me on Twitter at numeric8TEAPI, and you can subscribe to our newsletter at emergentbehavior.co. I will see you again a few days closer to AGI. Bye-bye.